Hi, in this video, I'll be going through what is a vector space, and this is really where we first touch base with abstract linear algebra. So, in our study of linear algebra, our first and most important object is known as a vector space. And a vector space is basically over a field of scalars, and the objects inside are known as vectors. And then you have an operation known as vector addition, where it is commutative, associative, and there's an identity to this operation known as the zero vector. And there is also an inverse which is unique to this vector for this operation. And this really means that this is a abelian group under addition. And then there's another operation that you add to it known as scalar multiplication, which really tells us how the scalars interact with the vectors. So the scalars are of course associative and distribution properties holds. So really, you think of a vector space, you have this abelian group, and then you assign how does it interact with the scalar multiplication. And really, it's really intuitive why we do so is because this allows us to form linear combinations inside the vector space, and you'll still be part of the vector space. So it is important to observe, as the definition states, that a vector is just a composite object consisting of a field, this set of vectors, and two operations with properties. And if we are not too confused by over what field, we can also still specify which field it is. So it's the vector space over the field F. For example, the vector space over R, which is the real numbers, is different from the vector space over complex, because now the scalars are whether in complex form or in real form. And the origin of the name is found below, but it's not much of significance, but it really gives us a more concrete and intuitive understanding about it. So how do we get these vectors in the first place is that we have a very common example of a vector space is known as Fn, or you can even think of it as Rn, where F is any field and we let V be the set of n tuples. Then we can define addition between the tuples as the following, and the product with the scalar is as follows. And we can verify again that it has the properties needed for a vector space, and so this n tuple space forms a vector space. And some immediate facts about vector space is that a scalar multiplied by the zero vector will always be the zero vector. And it follows from the distributive laws. So C bracket 0 plus 0 equals to C0 plus C0. And this equals to C0. So you can cancel out. And this leaves that C0 is just 0 vector. And if you multiply a 0 scalar to any vector, then it will also result in the 0 vector. Also, if A is any vector, then there is an inverse. And the inverse is actually just minus 1 times A, alpha. Also, we can now define what is known as a subspace, which is basically a subset of the vector space, which is still a vector space in itself, meaning that it's closed under the operations of its addition and scalar multiplication. And really, you can just check the axioms that the subset W is a subspace if for each vector the addition is inside, the zero vector is inside, and the minus alpha is inside, and the scalar will also be inside. This really just means that W itself is still a vector space. And one can simplify things further, and this leads us to having the subspace criterion, which states that W is a subspace of V if and only if for every vector and scalar the vector C alpha plus beta is again in W. And the proof follows that as long as W is not a non-empty subset such that C alpha plus beta is a vector, then of course it's a vector space. Because since W is not empty, there will exist a vector P such that minus 1p plus p is 0, so 0 vectors inside. And then you can just check the other properties will also be true. And conversely, if it's already a subspace, then we know this property definitely holds. So this is our subspace criterion to checking whether it's a vector space, whether a subset is a vector space. So some examples will of course be if V is a vector space, V will be a subspace of itself. And the 0 subspace will also be a vector space, so it's the set containing just the 0 vector. And Fn is a set of n tuples and this has a restriction such as the first coordinate is 0, will also be a subspace. The space of polynomial function O is a subspace of all the functions, and the square matrices, which is symmetric, meaning when you reflect along the diagonal if the same entries, then this will form a subspace of the original square matrix space. Another more interesting property is that we have the solution space for a system of homogeneous linear equation. So it's basically you collect together all the column matrices that satisfy Ax equals to 0, and we say that that is actually a subspace of all the n times n matrices over F. N times n matrices, you can actually just think of it as Fn. So basically what you're saying is that the solution space will be a subspace of the total Fn space. And to prove this, we just need to show that Cx plus y equals times A equals to 0. And this is immediate when you have this following lemma, which I'll leave you to verify. And by showing this lemma, it shows that when this is 0 and this is 0, this whole thing will of course be 0 as well. Because now you can expand this out to get Cax plus Ay, and this is 0, 0, so this whole thing is 0. So then this shows that the solution space is also a subspace. Next, we shall introduce more definitions, such as how you add two vector space together and is defined to be the set of u plus w, where u runs through u and w runs through w. And a lemma from that is to say that the intersection between two vector space will still be a vector space, and it actually the vector subspace that is contained in both u and w and is the largest one. So the proof of it follows that 0 will of course be an element of u intersect w, so u intersect w is non-empty. And we take a scalar and vectors inside this u intersect w. Because alpha and beta are both in u, C alpha plus beta is an element of u, since u is a vector subspace. Similarly, C alpha plus beta will also be an element of w. This implies that C alpha plus beta is an element of u intersect w, which then implies that u intersect w is a subspace. And if you want to show that it's the largest subspace contained in both u and w, you can just take any subspace and just show that it will be contained inside u intersect w as well. And the proof of the second one, that u plus w is a vector subspace, also follows from the subspace criterion, which I'll leave you to read on your own. And what you really want to show is that it is the smallest vector subspace that is contained both u and w. So now u is a subset of u plus w, and w is a subset of u plus w, and this is the smallest vector subspace that contains both u and w. So these are easy verifications to check, but gives us more examples of vector subspaces. One thing to note is that U union W is not a vector subspace, because you can just think of it in 2D. So you got this two-dimensional space. One of them is a line, and this is the origin. So the other one is a line. U plus W will be another vector over here, but it's not contained in the union of these two, because this is all the points here and all the points here. But now your next point could be here. Your next vector could be here, which is not an element of either of U or W. So U union W is not a vector space. Some things to take note. And the next theorem we have is a generalization of this, where here is an intersection within two vector space. Well, in general, we can actually say that the intersection of any collection of vector subspaces is also a subspace. And really, it is just doing what we have already done in showing that you just take into one coordinate and show that it's an element of U still. So what you do is, again here, you show that the vector inside here will also be a vector inside U alpha, W alpha, and it works for all alphas, and then so it must be inside the intersection as well. And so it follows that any collection of vectors in V, there is a smaller subspace which contains S. And that is a subspace which contains S and is contained in every other subspace containing S. And then we generalized our sum of two subspaces to a sum of n subspaces as follows. And we can also show that this will be a vector subspace containing this, and is by induction. And we say that this sum is direct when it satisfies any of the following statements, because they are equivalent. Basically, what it means to say that a sum is direct is that when you write U as a sum of UIs, so U1 plus U2 all the way to UI, then and you take this with another sum UI prime plus U2 prime, this must equal. In other words, it is saying that U1 it intersect U2 is just the zero vector, so it's trivial intersection. I'll leave it to you to show why is this equivalent, but it's not too hard to see how 1 implies 2, because you can just bring over. We also can see how 2 implies 3, and 3 of course implies 4. So I'll leave it to you to verify this proposition. And some concrete examples for us to visualize is that if these are all vector subspaces of V, then for any I not equals to J, Ui plus Uj will be a direct sum, because the intersection here is trivial, trivial, and trivial. And we can also now see that the sum of U1 plus U2 plus U3 is also direct, because 1 is the intersection between U1 and U2 plus U3 is 0, and so on. But we can now see that U1 plus U2 plus U4 is not direct, because U4 is not a trivial intersection of U1 plus U2. And so when we want to find whether a subspace is direct, we first need to show that it is a sum and that the sum itself is direct. Then we use this notation. So it's usually achieved by showing that every vector can be expressed uniquely. And lastly, we shall end off this video where we introduce the notions of vector spaces, and we can actually extend our our sum of vector spaces to an arbitrary set, which is infinite. But in this case, we need our sum to be finite, and then we just union all these finite sums. And that will be how we define the arbitrary infinite sum. But what we really like to note is that how we understand this infinite sum is that it is still the smallest subspace containing all the UIs. So that's all for this video, and I'll catch you in the next one. Please like, share, and subscribe, and I'll see you again. Bye.